Hello, this lecture will cover pages 211 through 214 of my lecture notes. Please print those pages out and have them in front of you as I present this lecture on Chapter 12I, Bode Plot Example 5. Up to now, our lectures have covered transfer functions that had a constant plus a first order zero, a first order pole, or a combination of all three: a constant, a first order pole, and a first order zero and a first order pole. We didn't cover any single S terms. We skipped over case 2A and 2B back in the previous lecture notes, and we went straight from the case 1 to the case 3A and case 3B. Let's go back and take a look at how to handle single poles or zeros that are at the origin. I want you to take a look here at example 211, or example number 5 on page 211. You're going to see a simple passive filter up here. Notice we put the capacitor up here, we put the resistor down here. That makes a big difference. It makes a huge difference where that capacitor goes. If the capacitor's up here, it's going to lead to a single S term in the numerator, and you'll see why in a minute. So here we have to come up with the transfer function, and I'm going to use the terms, just the variables C and R as I work through this, but I want you to notice that the transfer function is V out over V in, which is equal to that gain, which is R over X sub C plus R. Well, X sub C is 1 over CS. So keep in mind, you should be able to go straight from that circuit, any of these circuits that have R and C elements in them, to the transfer function. It's just the voltage divider rule. You just take a look at this and you take the resistor over this impedance, which is the X sub C plus the R. So it's R over 1 over CS, which is your X sub C plus R. I clean this up a little bit, multiply through by CS, a little bit of algebra. I get an RCS over RCS plus 1. Now I plug in the values for capacitance and resistance, and I get this transfer function here. That's the time constant form, no problem, but I can't extract my break frequencies. So I basically move this, I take this tau, which is 0.01, tau S, and I know tau is equal to 1 over the break frequency, and I just bring that to the bottom as a complex fraction, and I end up with this transfer function, and this is where you want to start from. I get 0.01 S to the 1 power. I'm going to put that 1 in there for a reason. And I get S over 100 plus 1. There's my transfer function. Now, before we go through and look at the Bode plot for that transfer function, let's take a look at this circuit and let's try to analyze it from a low and high frequency standpoint. At the real low frequencies, and what's the lowest frequency? Well, it's DC. That looks like an open circuit because, you know, DC can't go through these capacitors, ideal capacitors. So it blocks the signal. So at the low frequencies down here, this is omega. At the low frequencies here, you're killing the signal. The signals can't get through. At the real high frequencies, or when you get higher and higher in frequency, this looks more and more like a short because the capacitive reactance gets smaller and smaller based on the capacitive reactance equation, and it passes the signal through. It passes the signal through at a 1-to-1, so it's going to be a 0 dB. Don't forget, 0 dB doesn't mean you have a gain. It means you have a gain of 1. It means if you have 10 volts in, you get 10 volts out. If you have minus 3 volts in, you get minus 3 volts out, because that looks like a short. So there you get a gain at that point. At the high frequencies, it looks like a short, and you can pass the signal. So there's the response curves we're going to get. We'll use that as a check in a little bit as frequency goes higher and higher. Notice it's a high-pass filter. It's a passive high-pass filter. It passes the high frequencies. So, since we have a single S term in the numerator here, this K0 comes into play with two equations. The first equation I want to look at is you can't take 20 times the log of that and get a constant dB because there's no constant dB coming in up here. It's variable dB coming in. So the way we're going to use this K0 term initially is we're going to take 20 times the log of that K0 term, and we're going to get a minus 40 dB. That minus 40 dB is going to be the dB on the Bode plot at 1 radian per second. And we're going to use that as a check. We're just going to use this as a check, because what we're going to do, every time we have these single S terms in either in numerator or denominator, we're going to go straight down here. We're going to say if S sub n is a 0, as it is up here. It's S to the 1, n is 1, but it's in the numerator because it's a 0. If it's a 0, as it is in this example, the 0 dB intercept is given by this equation. So you're going to have to write this equation down. It's 1 over k0 to the 1 over n. Well, k0 is the 0.01. N is 1. And what this tells you is, this tells you the 0 dB intercept. It's 100 radians per second. That's going to be your starting point. Anytime you have single zeros or poles, you're going to have to go to a formula. In this case, this is the formula you use all the time if you have single zeros at the origin. And we have one of them here. If we have two of them, if that's s squared, that n becomes a 2. If it's s to the third, that n becomes a 3, and you're calculating your 0 dB intercept. So there's going to be our starting point, the 0 dB intercept. So omega 1, the first break frequency, is at 0 radians per second. Well, 0 is DC. So what that means is, way down here, it's coming in at an angle. It's coming in at a 0 at plus 20 dB per decade, slanting up. We've never had something like that before. The second break frequency is at 100 radians per second, and we know it's a pull up here, obviously, and it breaks down. When you begin your plots and have single S terms or double S terms or triple S terms, like we do here, you plot the 0 dB intercept first and use that frequency to label the magnitude axis. That's important. So let's look at the Bode plot. The Bode plot here is I transfer everything over, and I did here. Here's my transfer function. It's a single S term, so I'll put a 1 up here. Because I have that single S term, my K0 is still the 0.01. There's the 0.01 for K0. Now I could take 20 times the log of that, but that's going to give me a dB at 1 radian per second, like I said here on the previous page. But we're not going to write this down up here, because that's not how we're going to use this K0 initially. We're going to use this K0 in this equation here to get that 100 radians per second. So we come down to our plots, and 100 radians per second right here is going to be our 0 dB intercept. So we start at 100 and we go up and we label our 0 dB. And I put the 0 dB right in the middle here, and I went 10, 20 dB, and minus 10, minus 20, minus 30, minus 40 dB. This is 100 radians per second. That makes this 10 and this 1. It makes this 1K and 10K, and I'm labeling this obviously as omega and radians per second. So we know that our 0 dB intercept is at 100 radians per second. So we have a dot on our log paper right here. We also know the influence of that single S term has to be breaking in to that point at plus 1, which is 20 dB per decade positive. So all I do is go from this point, and I go back 1 decade to 10, and I come down 20 dB, because that's a slope of 20 dB per decade. I find a point here, and I find a point there. I could have done the same thing up here at 1K, and I could put it up to, 20 dB here. And I could have drew a line, this line here, dotted line here. All I need is 2 points, though. This has to be coming in at plus 20 dB per decade. So I know that point, and I know this point. I draw a dashed line. So the first line you're going to draw is a dashed line from here the whole way up through here. You know, one dashed line. That's the influence of that single S term. Now what about your pole? Well, you know what a pole looks like. It's going to come in here at 0 dB. I'm drawing it by itself now. I'm not worried about the constant right now, and I'm not worried about the single S term. I'm just doing that pole. And I know when it hits 100 radians per second right here, it just breaks down at minus 20 dB per decade. It's a minus 1. So how do I get that drawn? Well, I know that point. I come down 20 dB, and I come up 1 decade, and I get a point there. There's my 2 points. I put a dashed line in. Now, what's the overall response look like? Well, the overall response is going to look like you're coming in with a solid line up till you hit the intercept. You have a plus 1, and then you're going to hit a break of minus 1. It just takes this plus 1 out. We talked about that before, and it just goes back to 0. So there's my response. There's my response for this magnitude plot. Notice I'm coming in at a +1. I hit that break frequency 100 radians per second, and then I'm continuous at 0 dB out to infinity omega as it gets higher and higher. That's my phase plot. It's a high-pass filter. I want you to look at that. That's a high-pass filter. You knew that. It's a check. We did a quick analysis back here, so as long as you get the same shape, you know you're in pretty reasonable with it. You're okay with your Bode plot, at least the magnitude. But there's one more check. Remember this little technique I showed you? That K0 is 0.01. When we take 20 times the log of that, we got a -40 dB, and that's always at 1 radian per second. Whatever you calculate the dB through that constant, when you have single S terms, that's at 1 radian per second. Let's go back to my plot and let's take a look. At 1 radian per second, I should be at -40 dB. And I am. It tells me that that's a pretty good response, high pass filter. I will give you a note here that's really important. This is on page 112, really important note, and it says that if the S to the N term is a pull in the denominator, and it wasn't in this example, it was a single S term in the numerator, that was a 0. But if that is single S term like it's going to be in the next example is down here in the denominator, you have to use this formula for the 0 dB intercept. It's not 1 over K0 to the 1 over N. It's just simply K0 to the 1 over N. And that becomes the 0 dB intercept. That's your starting point. You have to be careful with that. Either you're using this formula or this formula. That's how you handle single pulls or zeros that are at the origin. So what do we do if we take a look at the phase plot? The phase plot here is on the next page. I laid out my radians frequency at the bottom the same way. I have my 0 degrees here. I put +45 + 90, -45 -90. My single S term, what does it do? Well, that single S term in the numerator there, that S in the numerator is j omega. Think about that, j omega. Well, that's omega at an angle of 90 degrees all the time. The angle's 90 degrees all the time. Omega can change, it's just changing the magnitude. It doesn't affect the angle. That's a constant, J. So I put a dashed line in at +90 because there's a single S term right here. If that was S squared, that would be a +180. If that's an S to the third, that would be a +270. You have to relabel these axes accordingly. You have to get smaller here in your increments per division to accommodate all that. But right now, we'll probably just go to single S terms, maybe double S terms, but that's the contribution of the single S term. It's a 0 in the numerator, so it's always +90. What about that denominator pull? That 100 radians per second. Well, we know pulls go from 0 to -90. So at 100 radians per second right here, I'm at -45. A decade down, I'm going to be at 0, and a decade up, I'm going to be at -90. So there's my contribution of the single pull term. So all I have to do is add those up to get a total phase angle, omega phi. Well, you can see that this just offsets this angle here, this phase by 90 degrees. You can just move this up. So we're going to be at this point in actuality. We're going to be at that point. We're going to be down 45 from this point. This is our reference now. And we're going to get back to that point. So our actual phase is going to look like this. That's our phase for that. That's our phase with respect to frequency. At the lower frequencies, below 10 radians per second, I'm 90 degrees phase shift input to output. When I get to 100 radians per second, I'm going to be at +45, and when I get at 1K or above, I'm going to be at back to 0. I'm going to be back to 0. Now, you can take both of these plots And you should be able on page 214 to use the Bode plots to find the voltage gain and the phase at 50 radians per second, at 100 radians per second, and then at 1K radians per second, and write them in here. And you don't have to do all three of them, but just take a minute. It doesn't take long to use the algebra like we did in the previous chapter, but take a minute to calculate the actual values and compare them to the above readings here from the Bode plots. And the comment you're going to find is, wow, if you do your Bode plots accurately, the Bode plots are the way to go. I want to point out one more thing that I think will help you as a check. If your transfer functions look like this, I'm going to make something up. And as the frequency goes higher and higher and higher, I want to try to find out where the angle goes. I'm just going to try to find out where this angle goes at the high frequencies. And you can use this as a check every time. If you take a look at this and S gets J omega, S is equal to J omega. Stay with me here. This is pretty easy. If S is equal to J omega, and omega gets larger and larger and larger, it basically just completely takes out these values here. And what you're going to end up with is S squared over S, which is simply equal to S. S is J omega, which is 90 degrees. So if you take a look at a transfer function that looks like this, its phase should eventually get to 90 degrees and stay at 90 degrees. Let's look at this transfer function. Well, if you let S dominate there, that's going to go to S squared. That tells me that you're going to end up at 180 degrees, and you're going to stay at 180 degrees. So that's where you should end up there. What if you have this? We had some problems like this. You can look back and check at this. What if you had something like that? Or the time constant form. This could be in a time constant. This is the break frequency form, but you could divide by 100. You could bring 100 out here. And you can bring the 1K out here, and you can get a constant like we did, and put 100 down here, and put a 1K, 1,000 down there, and make these both ones. I'm not worried about that. I'm just saying this is S plus 100 over S plus 1K. Well, as S dominates, that simply becomes S over S, which is equal to 1, which means no angle. This cancels out that. And we had problems like that. We end up with, they're back to 0. You get back to 0. So let's check this one. You have S over S. When S dominates here, you have S over S. You get 1. You should end up at 0 degrees. You should end up at 0 degrees. And you do. So if you look back over the previous 4 examples, you can do a real quick check on your phase plots that way, just to see if you end up in the right angle. That's another way you could check these plots real quick. And that concludes example number 5.